Good morning, class. Let's get going. Um, just a few reminders about where things are. This homework 5 that's due today. Many of you have already finished your homework, but if you haven't, it requires you to watch a lecture on ensembles and boosting and answer a quiz. You'll get 2 attempts at the quiz. I think it'll be the you get till midnight tonight, and then there's of course the usual late day. Also, homework 2 grades are have been posted on Canvas. If you have any questions about grading or want to, you should probably or just want clarification, um, you should, um, contact the TA who's graded your homework. You'll know who the TA is based on the comment that they leave in the homework on Canvas. And also, there's the rubric and the solutions that are available. Also, there's a project milestone that's due today. You need 2 more submissions on Kaggle. This is what happens if you copy paste slides week to week. Um, and also a short report. And by that, I mean like no more than a couple of paragraphs. Even bullet points are okay. That just tells me where things are. And if there are any updates, changes in your plans, or any problems that you faced, and any plans, what your plans are for the final 3 submissions that will be due in about a month, I think. Um, so are there any questions? Okay, so there's one, can't find homework 6 yet. Yes, it's not there yet. It will be posted most likely late tonight. And then, yeah, 2 more submissions on Kaggle. In the boosting lecture, I said that boosting mainly uses weak classifiers. Does this mean that more robust classifiers such as SVMs cannot be used? Not quite. I mean, you can use anything, but I do kind of mention that somewhere towards the end of that boosting part. If your weak classifiers are not weak, if your weak classifiers are really strong, then your ensemble might end up overfitting. Remember, every round of boosting increases the basically grows the hypothesis space for the final classifier. So if you're adding more and more of those, the risk you run is you might end up getting a classifier that overfits your training data. So you have to be careful with that. Doesn't mean that you can't use it. There's a slight technicality that you have to be careful about, and this came up in the office hours last on Tuesday. When you do use algorithms like SVM or even perceptron or any gradient descent style algorithms with AdaBoost, you have to be careful that your the classifier that you're learning at each round respects the distribution over the data. One way of doing that is most of these, pretty much all the algorithms that we of the SVM, perceptron, or neural network, this kind of family involves some update to weights. Weights are weights minus some learning rate times a gradient. Um, now let's say this is on this particular example. So X, Y, and W. Now suppose let's say that the weight for this example, we knew the weight for this example. Let's say the weight for this example is dt. Let's say xi, yi of I. Let's say we had this extra thing. One way, an easy way in which you can make the weight vector sensitive to the this particular distribution is to just make sure that the learning rate is controlled by this. So, or the step size. So you can just pre-multiply this with dt of I. So an example that's more important gives a larger step. And this essentially, this is called, this is one way of doing what is called cost sensitive learning. This is the minor technicality that you need to be aware of if you're using something like SVM or any of these gradient descent based learners with AdaBoost. Are late days allowed for the project milestone? Yes, they are. So you get to submit tomorrow if you are willing to give up 10%. what other algorithms are we going to be implementing in homeworks? Yes, this is a question that is useful for your project planning. So for your next homework, I've lost track of the number, 6, I think, homework 6, you'll be implementing SVM that we saw, and you'll be essentially deriving gradient descent for logistic regression and implementing it. So you will have 2 more learning algorithms that you've already as part of the library that you're building. So you can use those also for your project, or you can plan to use those for your project. Could SVM with a small number of epochs count as a weaker classifier? That's a possibility. It's worth exploring. You have to be careful that the notion of small number of epochs is relative. It depends on the task. It depends on the data. Depends on the noise in the data and all that. So I'm a little bit. I don't want to sound confident on this and say yes, this is always going to work, because maybe for your data set, a small number of epochs is enough to fit the data. So you have to be a little bit careful. So, okay, so a couple of other questions. There's a mistake. There was a submission mistake in checkpoint 1. Can that be corrected in checkpoint 2? Absolutely, yes. In some sense, the checkpoints are really to make sure that there's progress in the project. At the end of checkpoint 2, I need to see in total 3 submissions, 2 for checkpoint 2 and 1 for the previous one. If you have any corrections, yeah, go for it. So let's put that in the report also. Any corrections? Any tips on how to pre-process the data for things like binning? This is a question that came up a few times so far. So I'm going to spend a few minutes talking about this. Here's a nice trick for binning. Imagine that you have a feature. Let's say this feature is x1, let's say x1. And x1 is a real valued feature. So it takes values it lies on the real line. Now, what I'm going to do here is on this line, I'm going to just place examples according to their value of x1 first. So let's say we have an example here, a few here. Let's say these are the only examples we have. And in addition, each example comes with a label. So let's say I can, so the question now is, how do I bin this feature for use with a decision tree, for example? And what's a reasonable way of binning? Of course, you can do all kinds of things. You can just say that I'm going to randomly partition this thing into, not randomly, but I'm going to find just 3 locations and call this and this as my 3 bins. You could do that, but is there a more data sensitive way of doing that? One way of doing that is to note that every example, of course, comes with a label. So let's say this example is a plus, and this is a plus. Let's say this is a minus, this is a plus, so minus, and this is a minus. Let's say this is each example. So essentially, we have this one-dimensional thing. The way you implement this in code would be you just take that feature value, sort by the feature value, and then also look at the labels. Now, let's think about what would be reasonable places to bin. Let me add one more point just to, let's say we have a minus here. So let's think about what would be reasonable places to bin, to separate this example. Now, there is no reason to put a bin boundary here. So essentially say that everything less than this. There's no reason for that, because you will not have a single example in your data set with that particular partition in this partition. So there's no reason to do that. In fact, there's no reason to do any binning till maybe somewhere in this region here. And this is actually a good place to, exactly in between these 2 examples is a good place to put a partition, because look, the sign changes from here to here. So this is a good place to put a partition. There's no reason to put a partition between these 2 as far as this feature is concerned, because as far as this particular feature, x1, is concerned, this entire region here could be positive, because there's no evidence to suggest otherwise. So there's no reason to put a partition there. And then another place would be here. Basically, you look for when the sign changes and put a partition in the middle. Another one would be here, here, and that's it. So notice that the binning is essentially depending on when the label changes between neighboring examples along this axis. So you find all the features, find all the values for this particular feature, put them in an array, sort it, and then look for, you have to be careful with sorting so that you keep the labels around, and then put a partition only when the label changes, and that would be the bin. The location would be essentially the midpoint between these places and here. So this is actually a fairly reasonable way of doing things. There's a question: could such over optimizing of the bins lead to overfitting? It could, but here's the thing: as far as the ID3 algorithm is concerned, it is not going to ever pick a part. It's going to not prefer a partition. Let's give these partitions named 1, 2, 3, 4, and 5. This part, this threshold at 5 is actually not very helpful, because as far as this particular feature is concerned, it will there's negative on both sides. So in some sense, you will never get a pure split as far as this partition is concerned. You remember, ID3 is based on splitting the data in a pure way, which means bin number 5 or partitioning to the left and right of that particular line number 5 is never going to lead to any split that is pure. So essentially, this favors this notion of finding splits that are pure. So there is a risk of overfitting, but then that's where you do. After this, you have to worry about things like pruning the tree and all that. Would you end up repeating this for every single feature? Yes, you need to do this for every single feature, and you just you will have to think about how to make this more efficient. For example, maybe you just don't want to keep bins that are too small because you think that's most likely a lot of noise. It's also related to the next comment. If you have a lot of oscillation, maybe you want to introduce extra information by saying, look, there should not be so much oscillation here. Let me remove bins. Any partition that is within a window of, say, size 2 that's too small, you're not going to consider, for example. These are all design choices that you have to worry about. All of this should be done based on the training data only. Never ever look at the test data for any information that goes into your classifier, because then your test data is contaminated, because your classifier knows something about the test set. Don't even look at the test set for getting a count of the number of features. Personally, I like to separate it at the level of code. I don't even have code that reads the test set except once, and that's at the evaluation time. All right, are there any other questions? By the way, I think this particular binning strategy is implemented in, I forget which machine learning library, but some popular one out there. There are other questions? It looks like there aren't. So what we're going to do now is jump back into the lecture. Those of you who just who joined late, just a quick summary of the reminders. Homework 5 is due today, and the project milestone is also due today. And both of these, of course, you get late days if you want. All right. So today we're going to continue our exploration of Bayesian learning. And I'm going to use this as an excuse to introduce a new learning algorithm and a new family of, a new way to think about linear classifiers, it turns out. That's called logistic regression. Many of you have heard of logistic regression, and let's see what it is. Let's just to kind of make sure we are all on the same page. We have already seen many of the building blocks that are needed to understand logistic regression. We have seen linear models for classification. Importantly, this is for classification. And we've seen algorithms for training these kinds of linear models. We've seen SVM, we've seen perceptron. It turns out actually AdaBoost is also a linear model if your weak classifiers are just features. If we've also seen the idea of learning as loss minimization. And we've seen in the last lecture these two Bayesian learning criteria, namely maximum a posteriori estimation and MLE, which the E stands for estimation. So this is just redundant. So maximum likelihood estimation. So a logistic regression is kind of cool in that it takes ideas from all of these things and puts them together. So today's plan is we look at what logistic regression is. We look at how to train a logistic regression classifier. And finally, I'll connect this all back to the idea of loss minimization. So let's get started with what is logistic regression. In logistic regression is still a binary classifier. It's not even though the name has regression in it, it's a binary classifier. Your inputs are feature vectors, d-dimensional vectors, just like we've seen so far, and your labels are -1 or +1. We are given a data set S consisting of m examples. Each example is a labeled feature vector. So you have a pair xi, yi. So our goal of any reasonable model that we want to build, remember the goal of any model that we have encountered is something that takes your input space, instance space, so RD to the set -1 +1. So this is just the job of a classifier. But we're going to now slightly relax the problem and work with a different one. Sure, the output is still discrete. Either you have a -1 or a +1. But instead of predicting just the label, can we predict the probability of the y, the label being 1 for some example? So this expression here is just saying, if we had that, then we can ask if we had this, imagine that we had a function that can give us this probability. Then when a new example comes in, we can ask that function, what's the probability that the label is 1 compared to, maybe threshold it if the probability of y equals +1 given x is greater than equal to half, then you say the label is +1, otherwise you say -1. So if you had this particular kind of a rule, you can easily convert it into a decision like this by just thresholding at half, by checking which label is more probable. Does y equals plus have more than half the probability associated with it, or does y equals minus have more than half the probability? Of course, one of them has to, assuming equality is not happening. And that gives us a prediction rule. Now, so there's a question which actually is a fantastic segue. We're talking about classification, but the name is logistic regression because we're going to directly model this probability. We're going to this is awful notation, so I'll just say 0, 1. So we're going to build a function. We're going to train a classifier. We're going to train a model that instead of predicting a label, learns to compute the probability of the label being +1. While the original problem required us to take the input space into either a -1 or a +1, the new problem, the new setup that we have is going to take us, require us to build functions that take an input vector and produce a probability that the label is 1. In other words, we need to produce a number between 0 and 1 because the probability is a number. What this means is that even though originally we had a classification problem, we have essentially made this problem into a regression problem because our goal is to predict a real number between 0 and 1. So this is like the first sort of a mental switch that we need to make when we are going to logistic regression. We wanted to train a classifier, but in addition to building a classifier, we also want to produce the probability that the label is 1, which means we need to think about regression. Are there any questions? Also, does that answer your question, Han? There is a question about something about the environment. So I can, Ben, if you don't mind, I'll come back to that question because this is it's kind of or maybe one of my TAs can answer that question because it's just orthogonal to what we are doing right now. So what we have here is there are we need to the thing that we need to think about is we need functions that map RD to 0, 1. Why do we? So the question is, can we go over our motivation for switching to P of y equals 1 given x again? So the motivation is rather simple. So far we have always thought about classifiers as functions that just produce a label. Often what we might want is not just a label, but some notion of a confidence that the label is +1. Rather than instead of thinking of confidence, a natural language for that is a probabilistic one. So we can ask, what is the probability that the label is 1? And this can be a useful thing because if you still want to preserve some uncertainty, so if an example is assigned a probability of 0.9, so let's consider a few different cases. So suppose you have 3 examples, x1, x2, and x3. And let's say x1 is assigned, so this is example. And let's say the probability for x1 is 0.99, this is 0.7, and let's say this is 0.52. And just to make it complete, let's say x4 is 0.26. So if I had to, if you had to think about what is the best label for x1, it's almost certain that this x1 is a +1. In fact, if you just threshold at -1 at 50% probability, then x1 to x3 all have a label of +1. But clearly, there's a difference. If this probability was really a valid estimate of the probability, then x1 is almost definitely a +1, whereas x3 is extremely uncertain. And interestingly, the uncertainty in x2 and x4 is kind of similar. Both are roughly the same distance away from 50%. So essentially, we get this extra bit of nuance in our decision-making process by thinking about the probabilities, rather than just thinking about the hard decision. Because if you only look at the hard decision, we are left with there's no difference between x1, x2, and x3. They're all positive. So this is the motivation for thinking about probabilities. Once we, of course, you could have asked, why do we need probabilities? We could have had any scoring function. Probabilities, because they come with the heft of probability theory. We can start using ideas from probabilities to kind of even build trained learning algorithms, which is what we're going to do. So essentially, what we are left with is if we can build a classifier, if we can build a model that gives us that particular expression, we can always go from that to a decision by thresholding at half for a binary classification problem. So, and if your application demands that a threshold at half is not good enough, maybe you want at least 65% probability for it to be called plus, then you would probably say these two are plus, this one is uncertain, and this one is also uncertain because no, this one's a minus because it's outside of the probability of a minus in this case is 0.74, 1 minus 0.26. So These three things will get a label, and you have this luxury of even refusing to classify examples. So you get a little bit more. As we will see, there is actually a way of doing this even for things like perceptron and SVM, but it's nice to have another lens to look at the same problem. Once we have decided that we are going to start building probabilities, then effectively we are not building functions that produce a -1 or a 1, but instead we are building functions that produce a number between 0 and 1, and that's why it's regression. Does that clarify things, Christopher? Cool. So now that we have decided that we are going to we are going to look for functions that produce a number between 0 and 1, there's still a big choice. There are many functions that produce number whose range is the set 0 to 1. Which one do we pick? In logistic regression, in particular, it uses one class of functions that are that depend on the sigmoid function. So remember, HW here is needs to produce a number between 0 and 1. Logistic regression assumes, by definition, that the probability of y, so this is simply P of y equals plus given x. The probability of y equals positive plus 1 given x is the sigmoid applied to the dot product of some weights and the example. Let's unwrap this one step at a time. The first thing that let's go from inside out. The idea of this dot product is easy. This is exactly what we've been doing so far. So you have a weight vector W. When a new example comes in, you take the dot product of that weight vector with the example. Of course, there's a bias term also, which I have not shown here, but it should exist. And you get a number. And then, so that number is exactly here. And then you pass that number through what is called the sigmoid transformation. It's essentially a squashing function. The sigmoid function is just a function. The sigmoid of anything z is simply 1 over 1 plus e power minus z. And yeah, so what we define the probability of y equals plus 1 given x to be the linear function, which is w transpose x. But then you compose that, or you take the output of the linear function and give it to the sigmoid function. Sometimes it's also called the logistic function, which has this shape. So finally, what you get is the probability of y equals plus 1 given any example x is produced by taking the dot product of the example with some weight vector. And then the probability is 1 over 1 plus e power minus w transpose x. This is, as far as for now, think of this as just a definition. You may disagree with the definition, but this is somebody else's definition. Then let's see why this. We will see why this is a fairly reasonable choice, and in fact, we will see there are multiple interpretations for why this is a reasonable choice. We'll see at least one of them today, and if time permits, we'll see another one towards the end of the semester. Are there any questions? This is so far I have only defined things. I have not told you anything about how to get these weights. While you're thinking of questions, let me talk about this. Let's maybe also think about the sigmoid function. Not all of you have seen the sigmoid function before, and it has some interesting properties. So the first one is, let's think about what's the domain and range of this function. When, say, z, that's input to sigma, the sigmoid, is, say, 0, then you get e power z is 1, so you get half. So sigmoid of 0 is half. Let's think about what happens when you have sigmoid of a large positive number. So let's say 100. 100 is big enough for our purposes. It's 1 divided by 1 plus e power minus 100. e power minus 100 is such a small number that we can essentially ignore it. So this is approximately 1. And the sigmoid of minus 100, a large negative number, is 1 divided by 1 plus e power plus 100, which is such a tiny number because e power 100 is large. This is such a tiny number, you can approximate it's effectively 0. So the sigmoid function has the property, if in fact the sigmoid function, the range of the sigmoid function is 0 to 1, which works well for us because that's what we want probabilities to be in. And the other interesting thing is it as the parameter to the sigmoid function, as z gets larger, the sigmoid gets closer and closer to 1, which means this probability gets closer and closer to 1. When z gets smaller and when it becomes a big negative number, then it becomes closer and closer to 0. So if you want to plot it, it might look something like this. Ignore the 3/4 here. This is sigmoid of z. So, oh, I made a, yeah. So at 0, you get 0.5, and then it has this famous S-shaped, it's a famous S-shaped curve. There are other functions that have the shape, but this is a fairly commonly used one. So there's a question, what's the motivation for using this function? As I said, I could have defined the probability to be anything, any function that takes me from 0 to 1. Why do we care about this particular function? The first thing to note is that, first of all, it has this, there are multiple answers to that. One answer is that this is an approximation of a step function. It's if you think of thresholding at 0 to be the reason for changing the decision from a probability from 0 to 1, this is the sigmoid can be seen as an approximation of the step function. Another answer is that it naturally comes out of what's called the logistic loss. That's a surrogate for the 0-1 loss. We will see that perspective at the end. It also has some interesting connections to naive Bayes classification, and that's the perspective that we'll see hopefully in a different lecture. But for now, let's just take it as a given that we are using the sigmoid function, and we'll come back to this motivation question later. So this another useful property of the sigmoid function, which you may not see as an obviously useful thing right now, but it's going to be important when we are building, when we are training a model, is it's worth computing the derivative of the sigmoid function. The derivative of the sigmoid function is simply, the sigmoid function is just a function in one variable, so you can write d sigma over dz. You can work through all the math, but what you will see, and I encourage you to work it out and convince yourself that I'm not lying to you, the derivative of a sigmoid function is simply the sigmoid times the 1 minus the sigmoid, which is actually pretty cool. Because if you think of sigmoid as probability of plus given something, this is the probability of minus given something. So the derivative of the sigmoid function is simply the product of the probability of something being plus and the product of something being minus. I don't know why, but I find that to be somehow interesting. Okay, let's go back to actually using the sigmoid function. According to the logistic regression model, we have made an assumption that the probability of y equals 1 given x, and I've also put a w here because we can only compute the probability if we know the w. So the probability given a w for any example, the probability that the label is 1 is simply the sigmoid applied to w transpose x, which is 1 over 1 plus e power minus w transpose x. The probability that the label is minus 1 is simply the probability that the label is not plus 1, which means it is 1 minus sigmoid. 1 minus 1 plus e power minus w transpose x. I can simplify this. This simply becomes this expression here. So it's 1 plus e power minus w transpose x minus 1 divided by. So that these ones cancel out. So that's there is something else that's actually interesting here. So we have this expression. We can simplify that even more. So I can multiply both the numerator and the denominator with e power w transpose x. Sorry, yeah, e power w transpose x times this expression here in the box. So it is minus w transpose x these two things together multiply to give me 1, divide by, and I'm going to just multiply this and go through the whole thing. It is e power w transpose x plus 1. So if I want to write it in a way that looks very much like this, it's 1 over 1 plus e power w transpose x. So the only difference is there's a minus here, there's no minus here. So let's, if you don't really like my handwriting, here's a cleaned up version of the same thing. So the probability that the label is minus 1 is 1 over 1 plus e power w transpose x. The probability that the label is plus 1 is 1 over 1 plus e power minus w transpose x. You can combine both these things. Notice that when there's a minus, when we care about the label being plus, we need to put a minus here. When we care about the label being minus, we don't need to put a minus here. So we can combine both of these and say the probability of the label being some y is either minus 1 or plus 1, is 1 over 1 plus e power minus yw transpose x, which is exactly the same as the sigmoid of yw transpose x. This is interesting. Another reason why the sigmoid function becomes interesting is because once again we are back to our this familiar expression yw transpose x, and we will see why this this becomes a useful thing afterwards. So are there any questions? So what all we have done here so far is just I have written down how prediction works with logistic regression, and I have written an expression that is just a compact way of explaining what the probability of any y is, either plus or minus 1. Are there any questions? So far, all I have done is define things. A minor detail to think about is we care about p of y given x. Using, we've already seen the Bayes rule, right? I could have written this as p of x given y times p of y divided by p of x. I could have done this, and then instead of actually defining p of y given x to be this expression, I could have said, I want to learn these two expressions. Instead of learning a probability of a y directly, I could have learned p of x given y times p of y. And I could have built a classifier with that. That is a different family of models. Here we are directly modeling p of y given x rather than using the Bayes rule on this particular probability. Had we done the latter, had we done something like this, we would have actually arrived at effectively the naive Bayes classifier, and we would have arrived at generative models, but they're not doing that. We'll talk about that stuff later. So how do you make a prediction finally? So all we have done so far is define this probability. How do you make a prediction? Well, when a new example comes in, what you can do is you ask, what's the probability that the label is 1? Which we have given a weight vector, we know w, given, if you finish training, we know the weight vector w. So we can ask what's the probability of y equals plus given x and some weight vector, which is 1 over 1 plus e power minus w transpose x. And I can compare this to half. Now this is where it becomes interesting. So the probability, let me go over this in a bit of detail. So p of y equals plus 1 given x and w is 1 over 1 plus e power minus w transpose x. And I can now compare this to half. So predict plus 1 if this expression is greater than or equal to half. But now we can simplify this thing. So if that expression is greater than or equal to half, then I'm just going to take the inverse of these things. So then 1 plus, or you predict plus 1 if 1 plus e power minus w transpose x is less than or equal to 2. Or equivalently, e power minus w transpose x is less than or equal to 1. Okay, I can get rid of the e power, so I can take log on both sides. Or equivalently, taking the log, you get minus w transpose x is less than or equal to 0, or if w transpose x is greater than or equal to 0. So you predict plus 1 if w transpose x is positive. In other words, after jumping through all these hoops, what we end up with is prediction is exactly the same as the sign of w transpose x. We started off with this assumption, all these grandiose assumptions of saying that we're going to build a probabilistic model, and we chose a certain hypothesis class, namely this, the linear function gated through the sigmoid transformation. And then it turns out if you threshold the sigmoid at half, what you get is exactly the same prediction rule that we had with SVM, exactly the same prediction rule that we had with perceptron, and basically we have a linear classifier at hand. So what we had is, what we wanted to do was predict a label if its probability is more than half, predict whichever label has the probability more than half. So in particular, you predict plus 1 if probability of plus 1 is more than half. And it turns out if you simplify this in terms of prediction, then it's just predicting with the sign of W transpose X. So what we get is you can learn this probabilistic classifier. You can use a probabilistic criterion, which we will do in a minute, for learning this probabilistic classifier. But once that's done, you don't need to compute these probabilities anymore. You can just look at the sign of W transpose X. This is another reason for why the sigmoid transformation is pretty neat, because this particular property shows up. Another thing that also comes from this is, had you used some other algorithm for building your linear classifier, you could kind of, with a little bit of what I'm going to say next is not a formal statement. You can convert it into a probability, or what looks like a probability, by simply passing it through the sigmoid transformation. So there is this. There are a few interesting things that are going on here. I'll pause for questions because I feel like this would be a good stopping point for questions before we actually change gears and talk about learning these weights using a Bayesian formalism. Why does the sigmoid give a probability? This is a modeling assumption. I'm making an assumption that the probability is a sigmoid. There's no reason that it should. It's just a class of functions that I'm considering because it has the right shape, if you want. It produces a number between 0 and 1. It takes an input that is a vector. There are a few, there's another, there's a slightly different reason for this. And unfortunately, in a different semester, I would have actually gone into that a bit more. But because we've not yet talked about the naive Bayes classifier, I don't want to introduce that. And hopefully, once we get into naive Bayes, we'll revisit this question. The sigmoid also naturally comes out of a certain certain property of the naive Bayes classifier, it turns out. So there are a few different reasons, but for now, just let's make it a definition. I'm going to. The sigmoid does not give me a probability. I'm defining the probability to be the sigmoid and finding a set of parameters that best fits my data. So maybe it's not the right distribution. Maybe this is in some sense, this is a distribution assumption. This is a distribution over labels given the example. This is an assumption about the conditional probability of the label given the example. I'm assuming that they are distributed this way. Are there other questions? Is the sigmoid related to our transformation of Boolean spaces into linear threshold units? Not quite. Not directly, let's say. If you push me enough, I'm sure I can come up with some sort of a relation, but it's not directly related to how we have thought about Boolean functions and converted them into linear threshold units. Effectively, what we have is we have a linear threshold unit, and the sigmoid of that linear threshold unit is being treated as a probability here. Are there other questions? I can see you're all eager to jump into how learning works. So let's let's look at that. So what we've seen so far is we've seen what logistic regression is. Just the definition. It's just a class of functions. It's just an interesting class of functions for a few reasons. But the next thing that we should look at is like any class of functions. If you're considering them as a hypothesis space, you need to first think about what they express, and it turns out they are effectively linear classifiers. And how do you train them, and how do you make predictions? We've seen what they express, and we've seen how to make predictions. The only thing that's left is how do you train them? And just as a as an aside, we're going to kind of build up this thing, but not talk at the level of optimization. You'll be deriving the gradient descent algorithm for logistic regression as part of your homework with maximum a posteriori. So this is another thing that is worth keeping in mind is in the last lecture, we saw maximum likelihood estimation and maximum a posteriori estimation. Both of these are Bayesian criteria for building classifiers. We already saw two instances of MLE in the last lecture, two examples of it worked out in some detail. This would be the third of these examples, and we'll also see an example of map estimation, which we haven't seen so far. So let's first start with the simple thing, or at least the simpler thing, maximum likelihood estimation. We are given a training set. The training set consists of pairs of examples, X and Y. Y's are still -1 or +1. We still have labeled examples. I'm not, nothing has changed with the interface of our problem. The examples that we have are not probabilities, for example. Remember, what is the goal of maximum likelihood estimation? The goal of maximum likelihood estimation is to find a model. So let me write that here. It's to find model such that maximizes the probability of data given model. Maybe I should. It always happens. I always don't have enough space for the last few letters. So the goal of maximum likelihood estimation is to find a model that maximizes the probability of data given the model. This expression here is the likelihood of the data. So for logistic regression, the model is completely defined by a weight vector. So our goal of learning is to find a W that maximizes probability of S given W. S is our training set. So as always, we are going to assume that our examples are drawn independently from the same distribution. So they are drawn independently and identically distributed. They are IID. So we are calling the hypothesis a model because that's another term that gets thrown around. Effectively, these are almost interchangeable terms. So the question then is, We have examples that are drawn IID. How do we write down the probability of S given W using this piece of information? What can we say? Remember, S is really a set of examples. S is a set of examples. So what I would like is to somehow write down probability of x1, y1, x2, y2, and so on, given W. How do we use the fact that our examples are drawn independently and are identically distributed? How do we use the independence to simplify this expression? Can someone use the chat to take a guess? Notice that we have, so the question is, we have an example, we have a data set, P of S, S, which is a pair, x1, y1, x2, y2, and so on. And the goal of maximum likelihood estimation is to find some weight vector W such that P of S given W is maximized. The first step that needs to be done is I need to be able to write down this probability so that I can actually write down the maximization problem. So how can I simplify this probability here? Or how can I write down that probability using the fact that all my examples are independent from each other? Can I simplify this? You can multiply them together. This seems crude, but we can take what we get. In fact, that's exactly what we'll do. So probability of S given W is the weights that maximizes the probability of S given W is exactly the set of weights that maximizes the product of individual probabilities of Y given X, W. Now, this comes into place because examples are independent. So this is because of the IID assumption. Okay. Now we can do the usual thing. Instead of working with likelihood, we should never really work with likelihood because in practice, we get a bunch of small numbers, and that's you're absolutely right. Instead, we work with log likelihood. So we convert the product into a sum. And of course, this works because log is an increasing function and maximization still remains. So solving this problem is equivalent to simply finding the max over all the weights, the sum of log probability. So you have the probability there. Now it's become a log probability. So, okay, this is starting to probably look a little bit familiar, but let's maybe work out what this means. Remember that by definition of logistic regression, we know that the probability of yi given xi, w is simply the sigmoid of yi w transpose xi, which or equivalently, it is 1 over 1 plus e power minus yi w transpose xi. So I can take the log of this. So log P of yi given w and xi is simply, well, it's simply the negative log of 1 plus e power So, I mean, this just falls out of the definition. So I can now take this expression and plug it here. So solving this particular maximization problem is equivalent to solving this maximization problem, where I have just replaced log P of y given x with minus log 1 plus e power minus w transpose, y w transpose x. I've just unrolled the definition. So we are maximizing a sum of many negative things. So maximizing the sum of many negative things is identical to minimizing the sum of those things. So, but that's a minor detail. Effectively, just to make sure that we are all on the same page here, what we get now is our goal. Remember, the goal of this whole process that when we started was to find a probabilistic classifier. It's a discriminative probabilistic classifier. We'll see in a little while why I say discriminative classifier. This particular classifier says the probability of y given w comma x has this shape. In other words, it's the logistic model. It's the logistic model for p of y given x. P of y given x, so p of y given x is also, you can think of it as a posterior probability. It's a posterior probability of the label given an example. So effectively, you can think of maximum likelihood estimation with logistic regression is simply trying to find the most likely classifier under assuming that the posterior distribution of labels has this logistic form. This problem is essentially, we've just worked out, is identical to training a linear classifier by minimizing the logistic loss. So this expression is the same as min over w, the sum over I log 1 plus e power yi w transpose xi. So this thing here, the thing inside that I'm shading right now, is called the logistic loss. It's just another loss function. So this must look awfully familiar. We started off with this whole probabilistic criterion for learning, namely maximum likelihood estimation. And working through all of this, we have arrived at a minimization problem that just looks like another minimization problem, similar to SVM, where instead of summing over the hinge loss, we are summing over what's called the logistic loss. All logs here are natural log because we have e power. In general, anytime we see log, assume that it's natural log. Are there any questions before we talk about adding a prior or going to maximum a posteriori learning? Are there any questions? I mean, if you've not seen this before, this must look kind of tedious. So I want to make sure that we are all on the same page before adding another layer of complexity. And I'm happy to step through stuff again if you want. What happened to the mines? What is mines? Can you clarify the thing?
Probably the minus.
Where is the minus?
You
I left out the minus. That's my fault. Yes. Yes, there's a minus there. Thank you. When I change the max to min, of course, I can leave out, I remove this minus because that's why I changed the max to min, but the thing inside the exponent still remains. Yes. Thank you. Notice that most of what I have done so far is just a mechanical process of going from here to here is just mechanical. It's just algebra. The interesting parts are really, how did we get to this? Or really, how did we get to this definition? The fact that we're using maximum likelihood, and the question that many of you are asking, how are we going to solve this optimization problem? One easy way to solve this optimization problem is just to use stochastic gradient descent. I'm not going to work through the math. I'm going to, in fact, that's going to be part of your homework. You essentially have to derive, you have to set up SGD, where you assume that a single example is the entire data set. You compute the loss for that one example, and then you need to compute, the most important part there would be to compute the gradient of this logistic loss with respect to the weights and set up an update. And the whole thing with the learning rate and all that still remains in place. So from here, essentially, it's just an optimization problem. It's one of these optimization problems that does not have a closed form solution. So you need to do a procedural thing. So you can't take the derivative and set it to 0. You need to actually do numerically optimize. So this is just one way of doing maximum likelihood, estimating the weight vector with logistic regression. So what we started off with was we needed this. We wanted to find the most likely model. But remember, there are a couple of different Bayesian criteria for learning. So there is map. So let me start with MLE because we just worked through that. ML, in general, for the Bayesian thing, we want to maximize the probability of a hypothesis given a data set S, which is solving this maximization problem. We use the Bayes rule, and we say that this is exactly the same as P of S given H or proportional to times P of H. So now I can, with maximum a posteriori estimation, I can ask, find me the hypothesis that maximizes P of S given H times P of H. In the case of logistic regression, this is your weight vector. In maximum likelihood estimation, we assume that P of H is uniform. And so we simply want to find maximum over all H, P of S given H. This is the second thing is what we just worked out. In order to build this, we covered this in the last lecture, but the important difference between maximum likelihood estimation and map estimation is that MLE assumes that all hypotheses are equally likely. There is no prior information. But notice that this, when we talked about SVM, there was some prior information. We preferred weights that had, say, that gave you larger margins. Can we introduce such a preference into this process where we are learning logistic regression classifier? In order to do that, first of all, we can't anymore assume that P of H is uniform. If we have a preference over functions that is independent of the data, that means P of H is no longer uniform. You prefer certain hypotheses over others. The probability that this is your prior belief, so this is the prior, and this is the likelihood. Your prior belief that certain hypothesis is the true one is larger for some hypotheses than some others, even before you see any data, which means you can no longer assume that P of H is uniform. And this is what takes us from maximum likelihood estimation to maximum a posteriori. So the question then to think about is, what's a reasonable prior that we can use for these weight vectors? One, I'll come to this point about regularizer. For now, we are not talking about regularizers. We're talking about a prior. It's just a prior probability before seeing any data. What's the real one? What's the true hypothesis? So, in order to go to maximum a posteriori estimation, we need to add a prior. Let's assume that we have a certain reason to believe that each element, each weight in the weight vector, the weight vector is just a collection of many numbers, right? So W is a big vector of W1, W2, and the collection of D numbers. So each weight, W1, W2, in general, Wi, each weight is drawn independently from a normal distribution with zero mean and some fixed standard deviation, sigma. Which means P of W is, because every weight is drawn independently, I can assume that P of W can be broken down into P of, well, it's really this whole thing. And it can be written as the product of all these, the probabilities of the weights. And each one of them is just the normal distribution. So it looks something like this: 1 over sigma root 2 pi e power minus Wi square divided by sigma square. So I can use this. Now, how do I take advantage of this in order to build, in order to train a classifier? This assumes, of course, that each feature is independent from each other. And in fact, it assumes a little bit more. It says, in the absence of any data. Remember, the prior is all about, in the absence of any data, what do we believe the weight to be? What this is saying is, in the absence of any data, every weight is essentially centered around 0. So what it's saying is, if there is no reason to use a certain feature, because every feature gets multiplied with the weight, if there is no reason to use a certain feature, then set that the weight for that feature to be 0. Of course, there's going to be some noise, so maybe give it some standard deviation signal. So in the absence of any information, make the entire weight vector the 0 vector, because that's the one that is going to be the most probable one, because the normal distribution uh, um, attains its maximum at the mean. So effectively, this prior is saying, do not make any commitment about any weight vector, any element of the weight, any feature, in the absence of any data. How do we justify all these assumptions? How do you justify any assumptions? This is a how do you justify the assumption of a larger margin? There are this is in some sense saying, prefer to use as few features as necessary, and in the absence of any information, don't use any features. It's you can think of it as an assumption of parsimony in terms of hypotheses. So let's work through this process again. So what we're going to do now is we're going to build up to map estimation for logistic regression. The prior probability over the weights that we are assuming is this thing that we just saw. But as we are working through this procedure, what we will do is I want to kind of keep this maximum likelihood estimation thing on the slide, because it's worth seeing what changes from maximum likelihood estimation to map estimation. In MLE, what we did was we maximized the likelihood of the data. The goal of map estimation is not to maximize the likelihood of the data, it's to maximize the posterior probability of the model given the data. In other words, we want to find the most probable model given the data. So the posterior probability of the model given the data is P of W given S, which is proportional to P of S given W times P of W. So we want to maximize this product here. This is the standard. In some sense, this way of working is the bread and butter of Bayesian learning. Okay, so what we would like is to find some W that maximizes this expression, which is equivalent to finding a W that maximizes this expression here. So learning in this sense is really solving this maximization problem. We want to find argmax of P of W given X, W given S, which is the same as finding the W that maximizes the product of the likelihood and the prior. But the good news is at this point, we're almost done, because we have all the pieces that we need. The likelihood was exactly what we had before. It was this thing here. The prior, P of W, we've already written that here. All that's left is just to work through the math. Of course, there's a comment in the chat that there should really we should have P of W given S is P of S given W times P of W divided by P of S. I have not considered this at all, because we are only maximizing over W. So P of S doesn't depend on the W. So it goes away. It's just for normalization. So what we are now left with, we can now plug in all the different pieces and work it out. Just fair warning, the next few slides are going to be just full of notation, but the good news is we have really worked out all the details in the previous in the maximum likelihood case. So we're just going to essentially copy and paste. So of course, to make our life simpler to start off, let's take log. So solving this maximization problem, solving this problem is the same as solving finding the W that maximizes log P of S given W plus log P of W. Log P of S given W was this expression here. So we can just really copy and paste that. We don't have to work through that again. So that part is done. So let's think about the second term. So log of this expression is simply the sum over log of this plus log of this. I'm going to ignore the first thing here. This is just a constant. As far as the W is concerned, it doesn't. So I'm going to just say log of some constant. So this is I equals 1 to D minus. So log of e power minus W squared by sigma square is simply minus WI square divided by sigma square. I can pull out all these constants. So let's just expand the second term. I can pull out all these constants and then take the first thing alone. So the first one is I equals 1 to D of minus WI square divided by sigma square plus all of these together. By the way, this is C here, become a constant. Some constants, we don't care because it doesn't depend on W. So putting all of this into, typesetting this neatly, you can expand the log prior and you get this expression that is sum over all the weights of this quantity plus some constants. We're going to ignore the constants because we're just maximizing over W and the constant is not going to make a difference. We care about the argmax, so the constant is not going to matter. Okay, but look at this expression here. So we have, I'm going to pull out the minus and the sigma square. So minus 1 over sigma square, sum over I, WI square. W, the whole thing is a vector, W1, W2, till WD. This thing here is exactly the same as W transpose W. So this is exactly the same as minus 1 over sigma square, W transpose W. The dot product between W and itself is simply element-wise squares, the sum of the element-wise squares. So this expression is really the same as this thing here. So we can simplify everything and write it slightly more compactly as I'm maximizing the sum over the negative log 1 plus e power minus yw transpose x minus 1 over sigma square w transpose w. This is very much identical to the regularization term in SVM, but let's simplify this. Let's kind of rewrite this just a little bit more. Because maximizing this negative function, because this whole function is negative. By the way, the summation ends here. Maximizing this negative function is the same as minimizing the function itself. So I can clean up this whole thing and replace this max with a min, get rid of these minuses and make them a plus. And you get this expression here. Minimize the sum over the logistic losses or the log loss. And I think there's a bracket missing here. Plus 1 over sigma square W transpose W. So learning a logistic regression classifier with map, the map criterion, is equivalent to solving this optimization problem. This optimization problem must look awfully familiar. We've seen this before, and we've seen another thing that looks very much like this before. If I abstract out this expression, let me see if I can get a box. Yeah, okay. If I can abstract out this expression and just call it loss of yi, w, and xi, this whole thing is simply minimize 1 over sigma square w transpose w plus sum over loss. This is exactly regularized loss minimization. If this sigma square here makes you uncomfortable, I can keep this sigma square here and multiply throughout by sigma square. So there's a question here. Why are we keeping the sigma square term here? We've thrown out all the other constants. We've been careful about which constants we have thrown out. We have thrown out only additive constants. We can't toss out a multiplicative constant because it actually changes the function. I'll give you a simple example for that explains that. Let's say I want to maximize, say, or let's say I want to minimize x square. Of course, the answer is at the minimum happens at x equals 0. So let's say arg min. If we only care about the arg min. Okay, then what about arg min 2x square? It's still at x equals 0. Okay, what about arg min x square plus 2? Still x equals 0. In both these cases, you could have dropped the constant. Where you can't drop the constant is if you have x square plus x. Now, if I had a 2, you can't drop x. You can't drop the constant. So you have a multiplicative, um, what do you call this? If you have a multiplicative constant that is not, and there are other terms that also depend on the variable being optimized. So you can't drop the constants. So the next question to think about is, is this loss function convex? And the good news is, yes, it is. In fact, there's as an exercise, and in fact, for a homework, you'll be writing down the stochastic gradient descent for this. But as an exercise, you can think about proving that this is convex. The reason convexity is a good thing is because it's just one of those things that guarantees that learning will work. Of course, there are, in addition to a stochastic gradient descent, which you'll be inventing from scratch effectively, there are other learning algorithms that exist because it's just an optimization problem. There are multiple ways to optimize this thing. A class of functions that was more popular, maybe even up to a decade ago, but not so much now, is this thing called LBFGS. It's short for Limited Memory Broyden Fletcher Goldfarb Shano. It's an example of a class of methods called quasi-Newton method that uses estimate of the second derivative of this objective. It has become extremely less popular now simply because SGD methods are gradient-based methods. Just the first derivative alone is good enough. So the most commonly used approaches for these kinds of optimization problems today involves stochastic gradient descent or its variants. We'll see variants of this maybe even a week or so from now. So kind of just to quickly wrap up what we've seen, logistic regression is a classifier that predicts the probability that the label is 1 for a particular input. We have not seen this part, that it's a discriminative counterpart of the naive Bayes classifier. I'm hoping that we'll have enough time that we'll get to that at the end of the semester. It's a discriminative classifier that can be, we've not seen discriminative classifiers, but it's a classifier that can be trained either using the map estimate or MLE. In general, I would suggest if you're using logistic regression, just use map. It doesn't add any much more complexity. All you have is this expression here. It's a regularizer. Or alternatively, if you don't care for all these probabilistic interpretations, it's just a classifier that minimizes the logistic loss over the training set. Don't worry about all the other stuff because the problem. I mean, you can think about it that way also. We could, so just to answer that question on the chat, we could have assumed a hinge and you'd have gotten a weight vector, but it turns out that taking that and just giving it to the sigmoid does not give you good probabilities. There are calibration issues. We can talk about that offline. In the minute that's left, I'm going to just to kind of make sure that the connection is blindingly obvious to you. We have seen learning as loss minimization, but we've seen learning as loss minimization in multiple perspectives. In the ideal case, we want to minimize the expected loss, but we can't do that. Instead, we minimize the empirical loss, but that tends to overfit. So we've already seen these slides before. It overfits, and as a result, we add a regularizer that penalizes complexity. Or alternatively, instead of thinking of adding a regularizer that penalizes complexity, today we have seen another perspective of another origin story, if you want, for a regularizer. It's something that that comes from the prior over the prior distribution over the hypothesis space. So the prior distribution over the hypothesis space ends up manifesting itself as a regularizer when we are thinking of the optimization problem. And this regularizer, in particular for logistic regression, for example, it essentially takes the form of half W transpose W, or I think I missed a 2 somewhere, essentially W transpose W. If you want to kind of compare these various regularizers, we've already seen this before, so I'm not going to spend any time on it, but I encourage you to revisit. All these different regularizers essentially are different approximations of the 0-1 loss, which is the ideal loss function. The logistic regression regularizer that we just saw is something like that. All right, I'll stop here. We are a minute over time, so we shouldn't go more than that. The ideal loss, of course, is 0-1. Yes, Anthony, that's right. I'll stop here. Don't forget your homework. Don't forget the project submission, and we'll pick up on Tuesday, and we'll go from we'll probably start a new chapter on neural networks. See you all on Tuesday, and there will be another homework where you'll be implementing essentially logistic regression and SVM. All right, talk to you next week.